Good. So last week we talked about um, sort of the what vision does to in terms of recognizing objects. Um, this week we'll look at what vision does in terms of sensing motion, and you can see here. We'll talk about mostly this area here called MT plus, and this is an area, one of the big areas that is important in motion. It's the most prominent area. And you can see here, this dotted line here is the ITS, the inferior temporal sulcus. It's, again, a valley that goes along here. And that means anything underneath here is your inferior temporal lobe. That's where the fusiform face area is, and all kinds of other areas that are important in memorizing faces and places and other stuff. If you follow this up to here, and where it takes a dive to the top of the brain, is where you find the MT plus. And it's called MT not because it's the medial temporal sulcus, but it's because in the owl monkey, they originally found it in a location called MT. And out of habit, scientists try to keep to the same name, and they're still calling it an MT plus, even though it's nowhere near the human MT plus. But what does this do? Okay, so with your MT plus, here I am when I took this picture, I was standing at the corner of Richmond and Windermere on my way home, and you see all these cars moving, and you can tell what direction they're moving and what speeds. Without MT plus, this is what you see. Okay, you can see these stationary images. Okay, and you can't tell too well what speed anything is going in, and nor what direction. This this could be very dangerous if you're trying to cross the street. You don't know if the cars are stopped or not. Now, this is what you'd see if you only had MT plus. Okay, that is, you didn't have the area going under that recognizes what objects are. And you notice here that you see things moving, but you can't tell what they are because you don't have your what stream. You can probably guess that because you saw the previous slide, and it's sort of moving at the rate of cars, that they might be cars. But the other thing you can't tell is what color it is, because MT plus doesn't work in colors. All the color information is, again, going down the underside of the brain. So when you put these two things together, so this information here is going down the what stream, which can't recognize the speed of things. That recognizes that that's a car, but can't tell you what speed it is. And you put together the signal coming from MT plus, you see the normal thing. It's not that you put these two things together, too. That's the interesting part. You are aware of both these areas at the same time. There's no sort of creature sitting inside your brain that is able to see everything. You're simply aware of all the activity in your brain. Now, we mentioned before the signal coming up from the lateral geniculate nucleus first stops at layer 4C, and then some of it goes to these blobs that tell you color, and others go to these inner blobs, these wedges that tell you what orientation a line is, and they're important to tell your form. And this comes from, let's say, the fovea, and it's very shows you very detailed information. Now, the signal that's coming from the motion system is mostly coming from the peripheral retina, because that's where you notice the speed of things. And the signal goes up to another layer, first to layer 4C, but then it goes to layer 4B. And it's there that you find sort of simple cells that are, again, sensitive to motion in particular directions. And from there, the signal goes either directly to MT or indirectly through V2 and V3. It has two paths of getting there. Now, you saw that here, what happens is if this light here goes past these receptors at the right speed and in the right direction, because it lights up this one first and this axon is longer, it takes longer for this to get here. Lights up this one last and it's shorter. And so all these things meet at the same time in this cell and fire this cell. So by going at the right speed and in the right direction, you can fire this cell. If you go in the opposite direction, you can see that the action potentials arrive at different times in the output cell, and of course it doesn't fire. But there's some other cell somewhere in the brain that is tuned that particular direction. Now, telling what direction things are moving is not as easy as you might think. Now, you might think that all these lines are moving in different directions. And that's because all you can see about the lines is what you can see through the round hole. But if I look here, this line is moving actually horizontally. This line is moving horizontally. And this line is moving horizontally. But with only the aperture, you can't tell which way it's moving. But you assume that it's moving in a particular direction. You assume this one's moving up to the left, this one's moving up to the right, and this one's moving back and forth horizontally. You're making an assumption about which way it's moving. And that assumption is that you're assuming the line is moving perpendicular to the line itself, okay? You've got all these directions to choose from. You choose the one that's perpendicular. That's what you do in this situation, okay? And you can imagine that how this works is that you have simple cells that combine onto a complex cell, and if they're all oriented in this particular direction, and the the length of the axon is correct, you'll fire this complex cell. Okay? But there's another problem. Okay? Here you see a line, and it seems to switch directions. Okay? Here it's going up or down. Here it's moving left or right. Again, if you take away the hiding thing, you can see that it continues moving in the same direction. So what's the brain doing? Well, in some situations, it's also guessing where the ends of the lines are. So here, we can see the ends of the line. You can tell the line is moving horizontally. Here, you're from the fact that it's perpendicular, you're guessing that the lines are over, end of the line is over here. And in here, you're guessing that the ends of the line are at the very edge of this L. Okay? And for that reason, it's moving down here and to the right here. So you, in some ways, treat them as an object. Now, where is it that you come up with all these decisions? So we're going to do an experiment here. We're going to record from a cell in V1 and find out what direction it's sensitive to. And here, the lines are moving horizontally. That doesn't seem to get it activating much. When they're moving vertically, doesn't seem to care about those lines. But when I go down to the right, that cell likes it. Okay? Let's now move on to this area MT that we talked about. And look at that. Again, horizontally, doesn't seem to care. Again, vertically, it doesn't seem to care. But it seems to care in the same direction as before. So, where is it that your perception of that direction occurs? We saw that this cell in V1 lit up when you saw a line moving in this direction, and a cell in MT lit up for the same direction. And so with this particular stimulus, it's hard to tell whether it's V1 or MT that gives you the sense of which direction the line is moving. So scientists then came up with a different test. Okay? Here you see a line moving up to the right. Here you see the line moving down to the right. But let's say I put both lines on at the same time. Okay? Now, there's no line moving to the right. Okay? But what you see is this pattern moving to the right. So physically, on the eye, there's no line moving to the right. There's just this or this. But when you combine them, you see this. Okay? So the scientists then thought, well, why don't we try this as the stimulus? So here, physically, you're not gonna, you don't see, there is no line physically that's moving this direction, but yet you perceive that. Okay? So then when we try that stimulus on cells, here you see a V1 cell lighting up. Okay? Why is this? It's the same two cells we had before. It's lighting up because there is a line moving down to the right. If if we switch directions, okay, so here the perception is down, okay. Again, there is physically a line moving down to the right, okay, and that's why this cell is firing. Finally, if we do, I think it's this one, yeah, what? Yes, I realize that. I don't know. Maybe you can. I'll stop making funny noises in a minute. So I'll try to talk louder for a second. Okay. Here we perceive, okay, something moving down to the right. But physically, there is no such thing. There's just one line moving this way and another line moving this way. But we perceive this. And that's lighting up MT. So in V1, which is sending the signal to MT, physically there's no such thing as this. But when you perceive something moving in this direction, MT does light up. So MT is where you sense the direction of lines moving. This is quieter. I will try to program that noise to be less next year for the students. Yes, I think that's the problem. They before they weren't that loud. Okay. The other thing about MT is that it's sensitive to attention. Here we see this dot moving. Probably I should have drawn a line, but imagine the edge of this dot is a line that's activating this cell. And you can see that when the dot moves down, there's really not much activity coming. But when the dot moves up, the activity increases. Okay. Now let's try something else. We have two dots, and we say, pay attention to the blue one. Okay. Now the green dot is moving up, but you're paying attention to the blue dot. And so now the blue dot is moving up, and the cell lights up. But now we say, okay, pay attention to the green dot. And now it's firing when it goes up. And the cell stops firing when the blue dot goes up, but because we're paying attention to the green dot. So MT is very sensitive to where what characteristic you're directing your attention. So it's sensitive to direction motion, but also what you're attending to. So when you're crossing the street and you're not attending to cars because you're looking at your cell phone, guess what? So basically, you're blind to the dot you're not paying attention, and you're blind to the car that might be heading towards you. Now, how is MT organized? Well, there's the area MT. There it is unfolded, and you can see it's got columns, and each column is sensitive to part of the retina. So this square here is sensitive to one part of the retina. This is sensitive to the adjacent part of the retina, and this is another one adjacent to that. But this one square is this whole thing, okay? And in that little square, there are little sub columns, each sensitive to either of two things. One is, you can see the arrow directions varying, so that's the direction of motion. And you can see the color varying, and this is the depth of whatever it is that you're looking at, the line's depth. So both depth and direction are being encoded within each of those columns. Again, that a cell is firing is what tells you what its direction and depth is. Okay, so it's a particular set of neurons that gives you that sense. Now, beyond MT, there's two areas. That's why this place was called MT plus. So because MT plus contains both MT itself and something called MSTL, which is the lateral part of MST, and the dorsal part of MT. So a lateral and dorsal part. And these two things do different actions or different. This part here, L, the lateral part, senses the speed of objects, okay? How fast is this ball in tennis moving? How far is it? What direction and speed is this airplane moving? It's involved in something called pursuit movement. So when I follow my finger back and forth, it's the signal that's driving this movement. And we'll talk about that in the second to last lecture. So we'll discover more about this. A very different thing happens in that dorsal part of MST. It's involved in your perception of what direction you are moving. So when you're in a car and you're heading a particular direction, different cells will light up for different patterns of motion on the retina. And the different patterns of motion on the retina tell you which direction you're moving in. And because the pattern on the whole retina is important, this place here has a property that it has input from the whole visual field, the left visual field and the right visual field. We saw before that fusion FFA had the same property, because when you look at the face, you want to see the left side of the face and the right side of the face. Well, here too, to discover what direction you're moving in, you have to know what's happening from both sides of the retina. And we'll see in a moment why that's so important. Okay, here you can see. We'll show you some patterns, but before we do that, this sense of motion that this signal is providing is what causes you to sometimes missense things. Like you're in a car, you're stopped, there's a car in front of you. And often when it starts moving, you get the mistaken impression that you're moving backwards. Okay? Or you're in a subway car, and the train beside you, the subway cars beside you in another train start moving. You sense that your subway car has started to move. Okay, and it's because of these patterns of motion in this area. So when, for example, I turn to the right, forward works, you can see that this pattern of motion appears on your retina. These lines spreading out, starting from where you're looking at and going out to the peripheral. When you're moving backwards, the opposite pattern appears. Things are heading towards the fovea. The motion is heading towards the fovea. Yeah, in a moment we'll have left and right moving as well. Okay. So when we turn, maybe not. Yeah, okay. So this pattern appears when you turn left. Let's say you tilted your head. You'd have this pattern on your retina. If you tilted your head the other way, you'd have this pattern appearing. And you can imagine you could be going in hundreds of different directions, and each one would create its own pattern. And again, MT plus or MSTD is composed of different columns, and within each of these columns, cells are sensitive to a particular direction. So when one column lights up, you sense that you're going in one direction. Let's say in this direction. Another column would light up for any of these other directions that I described. Okay, let's talk about motion parallax. Now, we talked about, I think it was in the first lecture, or the second lecture, about disparity between the two eyes. Okay? Well, the disparity between the two eyes is good, very accurate for things up to about an arm length away. When you get more than an arm length away, it's hard to measure the difference between the two eyes. The difference becomes very, very small. So then you start using other patterns. I don't know if you guys ever watched chipmunks try to jump. If you look at them carefully, they bob their heads up and down. And from bobbing their heads up and down, they can sense how far away things are. Okay? And they're using this thing called motion parallax. So when you move your, let's say this is them moving their heads up and down, and they can tell by how fast things are moving on their retinas, whether they're near, as this dot, the square is, you can see it's moving more than this one here. So whichever one moves more, that one's closer. So they can measure distance that way by how fast things are moving on the retina. If now, but the other thing that complicates matters is often when you move your head back and forth like this, your eyes turn. So that creates a problem because it depends where you're looking. That determines how fast things will move on your retina. So here we're looking at the near object. We're looking at the square, and it looking at what is actually appearing here. Yeah, it stays stationary on your retina. You can see that the fovea is this little yellow bar that I've drawn. Okay, the little yellow bar stays where the green object is, and the red object is moving back and forth on the back of the retina. Here you're looking at the red object, the one that's further away, and now the green object is moving on the retina. So the brain has to take into account uh, how much the eye is moving. Okay? How does it do that? Well, it's important because we want to know if you're looking at an object, like here the lion, whether it's moving or your eye is moving. Kind of crucial for survival to figure that out. So a fellow by the name of Helmholtz, he was a physician and a physicist. And about 100 years ago, he came up with a theory of how this happens. And what the theory is that there's a signal that goes to the eye to move the eye. And there's a signal coming from whatever you're looking at that causes slip on the eye. Okay? And the brain sends a copy of the command, and that's called a corollary discharge, to a place that's called a comparator. It compares these two signals. So it compares how much things are moving on your retina and how much is being produced, how much the eye is moving. And from that, you can figure out how much the object is moving. So you can see here, okay, that in this case, it figures out this is how much slip is being produced. This is how much signal is being produced by the motion of the eye, and the two are equal. So all the slip here, all the motion on the retina, is being produced by the eye movement. And when that's the two signals then cancel, and the brain decides, the lion is still. And in the problem set, then we can look at other combinations of things that can happen on the retina and what you can decide from there. In this case, there's no corollary discharge, so the eye isn't moving. And the brain sees slip on the eye, and then it says, okay, all the slip is coming not from my eye movement, but from something moving. So the lion is moving. And the same thing happens not only from slip caused by the side-to-side things, but when you move closer or farther away. So this corollary discharge comes not only from my movements, but from any body movements that you're making as well. So any movement can be compared to what's happening on the eye. So all the structures that cause motion send signals to this comparator. Okay, another topic. Another topic is motion after effect. I would like you to stare at the center of this circle. It should be big enough for most of you. Okay, start, and don't move your eyes, keep staring. What happened to the face? Hmm? I had a sense of motion of the face. Let's try that again. And this time, instead of looking at the screen, look at your hand. Okay, keep looking at the thing going round and round. And then when I stop, look at your hand. Okay, stop. You should, if you're lucky, see the hand moving. And if you looked at somebody else's face, their faces will move as well. So that's called the motion after effect. And the question is, what causes it? Well, one misinterpretation is that it's happening because your neurons are getting tired. Well, neurons don't get tired for no reason. Okay, it could be this property of adaptation. Okay, we saw that the brain is interested more in things changing. So if things stay the same, the signal gradually um, dissipates, and then when it stops, you have a rebound. Okay, and things that aren't moving you start sensing that they are moving. But there's a better reason for this happening. Okay, you can imagine. We said before that this sensing, what you have in MT is all these cells, and each one is sensing motion in different speeds and directions, and so it's looking at this motion and figuring out what speed it's going in. And what's happening is that which cell is measuring that speed changes over time. Okay, so the cells that have a similar speed to this moving object become sort of crowded together. I've visually sort of drawn them closer together, and by that I mean that they measure smaller changes in speed. Okay, when they were more separate, they measured bigger changes in speed. When they're closer together visually, as they don't move together in the brain, they just move together on this picture. So the closeness symbolizes that they're measuring different speed amounts. Okay, what happens to this cell here? This cell here normally fires when you see something moving in the opposite direction. Okay, something slowly moving in the opposite direction. We fire this up, and you can see that this cell here, which normally sense that things are moving in the opposite direction, suddenly gets pulled by this recalibration into this point here, which is measuring that an object is stationary. So then when we show that cell something stationary, it fires up, and you sense that something is moving in the opposite direction, like the face was, like your hand was. Okay. What's interesting about this? Well, from the motion of these dots, we're able to tell that this is a lion. And again, look at what happens when the motion stops. The lion gradually disappears from sight. Okay? So here, what's happening is MT, which is sensing the motion, is sending a signal to LOC, which is part of your watch screen, which lines belong together, and because of their motion. Okay, they give you a clue to LOC which lines belong together. They bind those lines, and those lines then are used. That signal from MT is used by LOC. Say, that's a lion. Now, what's interesting about this? What most of you should see a white square moving back and forth. But actually, there is no white square moving back and forth. All I've done here is I've drawn a white square here, and then I take it away and draw a white square here. And actually, there's no white square here because all I've done is put these corners in these circles, okay? And there's no white square here because all I've done is taken away parts of these lines. So information is coming from these objects that are drawn here and objects that are drawn here and telling MT or misleading MT as to that something is moving. So now a signal is going from LOC to MT, generating a sense of motion. So what that, in the first case we saw a signal coming from MT, now we're seeing a signal going from LOC to MT. So that tells us an important thing, that things are sending signals back and forth to each other. Your whole brain is interconnected. Every area that talks to one area talks back to the other area. There's always feedback going. Okay. Now, you see here two sticked objects, and really it looks like some human or something like that, but nothing much different from each one. Here, okay, well, it could be that there's simply a statue, okay, that's rotating. It might not be something alive. Here, you can see definitely that it's probably something alive because joints are bending and moving. And that sense of something alive moving is called biological motion. You're tuned to these biological motion. And the area that's responsible for this is an area called STS, the superior temporal sulcus. So you've got LOC that sort of tells you that, oh, there's a human-like figure that sends a signal to STS, and a signal coming from MT, the signal of motion that's going to STS. And from the two of them, you're generating this idea that, there must be a human or something that's biological. Okay? And the same structure we'll discover is used to lip read. Okay? You can discern what people are saying in large part by just reading people's lips. And if you study hard, deaf people can learn to read lips and tell what people are saying. So in summary then, we saw early that we had two mainstream, a where stream and a what stream. And some people are suggesting that this thing that we talked about here is a when stream. They're given another name. Okay? But from its characteristics, it's more like a where stream in the sense that it's receiving information mostly from your peripheral retina. And then your peripheral retina doesn't deal too much in color, and it uses these magnocellular cells that we talked about before. And that's it.